Hi, everybody. I had some technical difficulties this weekend, and I'll explain in detail on Monday. But if you get an opportunity to see this on Sunday night and do the homework, awesome, because I think it'll lighten your load during the week. If not, if this is getting to you too late and you need to do it on Monday night, that's what it will have to be. And I do apologize for not being able to put it up earlier, but like I said, I had some problems. Okay, so we're going to start to talk about Charles' Law, even though we've introduced it and we've talked about the relationships. There is a fancy name, and we discussed this, I think, last Wednesday night, that this scientist is the one that came up with it. Okay, and it deals with the volume and the temperature of things. So I'm not going to read this directly to you, but you can see right here this special little symbol and this notation here that absolute temperature is a positive temperature scale. So in other words, the Kelvin scale is a positive temperature scale. And we started collecting data in school using the Gauss meter, and we are looking at what the relationship between volume and temperature are by holding the volume constant. Actually, we're using temperature and pressure, but again, we're going to figure out how temperature really has to be in the Kelvin scale. So with all of that being said, please understand that when you do mathematical problems with the gas laws, you always have to use Kelvin temperature. So let's take a minute to look at the fact that we've learned that volume and temperature are directly proportional. We talked about some things. We talked about the idea that if you get your balloon at a party where it's warm, the gas completely fills the shape of the balloon. And then if you go outside where it's cold, all the molecules will slow down and as a result take up less space, and your balloon will not be filled up nicely. So that's the direct relationship, that if temperature's high, volume's high, and that if temperature goes down, volume goes down. So that we call direct relationship. And remember also last week I showed you what the math looks like, the formula. So you have to understand that volume, oh, hold on, I forgot to put the pen on. Okay, that volume equals temperature times a constant. And remember, the constant is N, which represents the number of moles, and pressure. Okay, so those are your two constants. And what this can turn into is the understanding that volume is directly related to temperature. Okay, it varies directly with temperature. And we end up writing that this way: volume equals temperature. And we will get to the situation where we'll work on the math in a second. So we'll explore more this week how and why the temperature has to be in the Kelvin scale. But for now, let me point out something quickly. So as long as you start to understand that Kelvin is the temperature scale, we can have 0 where the x and the y axis intersect. And when we have 0, that means that we can create a direct proportion, so that say we were to double or create a situation where we had 200 Kelvin, well, then we would have our volume be at a set number, and we could plot the point of 200 and the volume. And then if we were to double it, we would have 400 Kelvin, the temperature. And then because it's directly proportional, which we're talking about, then we would plot our point here, and we would create a scenario where we have this line that goes from the axis point through the other points, and they're directly proportional. So this line represents a volume equals a temperature line, because as much as the temperature goes up, the volume goes up by the same amount. So that's why it's so important to use Kelvin, so that you can get that direct relationship. Okay, let's go to the first question and start working on the problem. So we're going to use all of our variables that we know about: volume, pressure, temperature, vice presidents, which is a way to remember it, over teachers, equals vice presidents over teachers. And the reason we have two of these setups is because we take the current situation, what's described in the problem, and then the future situation, which is what the problem is telling us the conditions are changing and becoming. So if we read this question, it says, if the temperature of a 27-liter smelly gas is decreased from 27 degrees Celsius to negative 173 degrees Celsius, what's the new volume? Well, based on what we just said, we're not able to plug the Celsius temperatures in. Can't do it. It has to be in Kelvin. So I'm going to hit stop a second, and I'm going to convert these numbers to Kelvin. You hit stop and see if you get the same numbers. It's just a simple little formula. Let's see if you remember what it is and if you can do it. Okay, so you can see here that I used the formula Kelvin equals degrees Celsius plus 273. I took the 27 degrees Celsius and I added it to 273 to come up with a temperature of 300 degrees Kelvin. And then I took the minus 173 and positive 273 leaves you with 100 degrees Kelvin. And those are my two temperatures. So now you go and do the problem. Okay. So we're looking at the problem, and we have to use the formula to plug in the Kelvin temperature and a volume. So we have temperature and volume, but what about this pressure that's in this formula that takes all three variables together? When the problem says what is the new volume at a constant pressure, that's when we can cross off the pressure and know that it is not involved in this particular problem. So we just simply put a little line through it. Oh, I'm sorry, I'm fighting with this. All right, we're going to cross off the pressure. Let's see if I can do it. Oh, I did it. Cross off the pressure. So now we're only using the initial or the beginning volume and temperature, and we were given a new temperature. The question is, what will the new volume be? So the initial volume is 27 liters. The initial temperature was 300 degrees Kelvin, and that all equals the new volume, which we don't know what it is, and the new temperature is 100 degrees Kelvin. Okay, so now we have everything set up. Now we have to solve for this. In order to get rid of this 100 over here, I have to multiply by 100 over 1, and I have to multiply by 100 over 1. Okay, so what you cannot do is just solve for this in the way that maybe you're accustomed to in the past. What I need to ask you to do is do the setup. I need you to combine things that are alike. So I need you to combine right now for the setup over here. I need you to put the 100 Kelvin over the 300 Kelvin and multiply it by the 27 liters. And you could put that over 1 because now you'll understand it's over 1. And this equals the volume, because this is what the Regents asks for at times. They just want to see that you know how to read a question, do the conversions, set it up, and show them that this is what it takes to get the answer. Or other times they'll actually ask you to come up with the answer. So I'm going to hit pause and type some stuff into my calculator. You do the same. Okay, so I have confidence that you can plug into the calculator, and a lot of people got 9. So that's fine, except the question is, did you still remember to pay attention that you've got 2 significant figures here, 2 significant figures here, 3 significant figures here? So I can't put my answer just as 9 liters. I have to put it as 9.0 liters. So the answer is 9.0 liters. Also, make sure that this really makes sense to you. Remember that we set this problem up initially to be 27 liters over 300 degrees Kelvin, and the 300 got changed to 100. So I think it's easy to see that 100 is only 1/3 of 300. And I think it's also easy because think about 3rd grade, your multiplication, that 9 times 3 is 27. So 9 is 1/3 of 27 also. So it's really showing you that direct relationship. And that's always a good thing to be in the habit of, to check your answer. Does my answer make sense? I know these things are directly related. I know that if 300 goes to 100, that goes down by a third. To 1/3, and if I have 27 here, what should the answer be about? Think of it in your head, and then plug everything through methodically. Don't make any mistakes. Make sure you go into your Kelvin degrees. Make sure you combine your like terms over here. Make sure you set it up properly. Get your answer, and then always double check your answer for yourself. So you can all try number 4 by yourselves and see how you do.